Okay, so we've been talking about kinetics here in this last chapter. Again, kinetics dealing with really the rates of a chemical reaction, how fast or slow a reaction takes place. Um, we talked about a couple of different things up to this point. We talked about the rate expression. The rate expression, again, is that one that you can basically use to figure out how reactants are changing over time, how products are changing over time. That's the one that sort of looks like the rate is equal to -1 over A, change in concentration of A over the change in time. Again, the negative if A was a reactant, positive if it was a product. We also talked about the rate law, which deals with just the reactants involved and kind of looks like the rate is equal to k times a to the x and b to the y, for example, where k here is our rate constant. And that's sort of a constant relationship that relates to how sort of fast or slow the reaction is happening. The x and y, as we talked about, are what are referred to as orders. And again, that's sort of the proportion of those guys. They're needed to sort of maintain a rate. This is the one that we basically figure out experimentally by doing sort of that rate 2 over rate 1 sort of calculation, like we've done a number of times in some examples. And again, this usually is accompanied by a table of information, table of concentrations, table of initial rates. And then remember, when you go to that table, your goal is to really choose two entries where one remains constant and the other sort of concentration varies. And that allows you, again, to get things like, for example, for is equal to 2 to the x, where x would equal 2. And you kind of experimentally figure out those orders. Once you experimentally figure out the orders, you can figure out the overall order of the reaction by adding the orders together. And once you have really the completed rate law with those orders, you then could go back and really solve for the actual value of k. And remember that when you go to do that, pretty much you could choose any entry you want in the table. Because it's a rate constant, it should be a constant value regardless of what entry that you put in there, and you should be able to come up with sort of the value of k. Now, we also ended up talking about some different types of orders, or started to talk about some different types of orders, and we got through sort of first order reactions. And first order reactions basically can occur, um, where you have, for example, the rate is equal to ka to the 1 in this case. And one thing that we talked about is actually the value of k, not necessarily the value of k, but the units that we associate with k, which if we rearrange that rate law and solve for k and kind of just put the units in, we get the typical units of a first order reaction, which is 1 over seconds. Again, it doesn't necessarily have to be actually seconds, but some type of unit of time, 1 over hours, 1 over days, weeks, seconds, minutes, something like that, is typically what we see for a first order reaction. Why that's important is because they will not always tell you that you're dealing with a first order reaction or second order or zero order, which we'll talk about today. But they will give you sort of the rate constant in the units, and you should know based off of those units that it is first order. It's important because the first order one actually has its own sort of dedicated law for our equation for concentration versus time. And that's the natural log of A is equal to natural log of A naught minus KT. This A here is sort of your final concentration. That's your initial concentration. K is the rate constant. And T is time here. So those are important sort of guide there. Also, it has its own half-life equation, and that is the half-life is equal to the natural log of 2 divided by the rate constant. And the half-life is, again, the time it takes for half of whatever you started with, obviously, to sort of disappear and stuff like that. So When we look at this, though, we could rearrange this equation to the natural log of A is equal to minus KT plus the natural log of A naught. And when we rearrange this, this is based on a straight line, y is equal to mx plus b. That means that on the y, what we typically graph for first order is the natural log of A. On the x is t, and that gives us our kind of straight line there that we would expect, where the slope of that straight line is equal to the rate constant. Any questions on any of that there? Okay. So as a reminder that as I sent out in the announcement, in terms of the final, in terms of this chapter, up to what we lectured on last time, is what you need to know for the final that's on Thursday. So whatever we're going to lecture on today, outside of first order, we may do another first order example or something like that. But anything past sort of first order, you will not be responsible for on the final. Okay. So let us take a look and see where we're at here. So I think this is where we left off. And again, we sort of jumped the gun a little bit there last time and really did talk about sort of the half-life equation. And the half-life equation, again, is specific for first order, is the natural log of 2 divided by k. And so why don't you take a moment here and do the one on the bottom. If the half-life of it decomposes at a rate constant of 5.7 times 10 to the minus 4, what is the half-life? And how do you know it is first order? So take a second or two there and see what you come up with. Okay, so let's take a look at this one here. What is the half-life? And we would use obviously the half-life equation that we just saw there, which is T1 half is equal to the natural log of 2 divided by k. This is the rate constant, so we basically just need to plug it in there. Natural log of 2 divided by our 5.7 times 10 to the minus 4 reciprocal seconds. And if we do that there, that's going to get us natural log of 2, which is also 0.693. You'll sometimes see it written as 5.7 to the minus 4. And I guess if I punch that in right would be good. Minus 4. It gives us about 1,216 seconds. The seconds come to the top when we do the division. And if we want to do a little sig fig action there, maybe about 1,200 seconds would be appropriate based on the two significant figures that we have going on there. First off, any questions on that one there? As I mentioned earlier, we kind of know that this is first order because of the units associated with the rate constant. And again, those units are reciprocal seconds, tells us it is first order. And that's a really important thing in terms of kinetics. Like I mentioned a number of times, a lot of times they really will not, with like a neon sign or something like that, tell you, sort of what the order is, but they will give you that rate constant and you can try to figure it out that way. Any questions on that particular example there? So here's just a graphical representation, obviously, of half-life. And in the term of sort of first order, again, half-life in general means, again, the time it takes for half of whatever you started with to go away. As you see, the green dots sort of get half small as you keep going through each half-life. In terms of first order, it is only based on really the rate constant. So the rate constant really determines how fast sort of the half-life would be. So why don't you take a few minutes here and try this one. We want to know in this particular reaction here, it's first order with a rate constant of 2.9 times 10 to minus 4. What is the final concentration if the initial concentration is 0.0225 after 865 seconds? So take a couple minutes to see what you come up with. Automatically tell us that we do want to use the specific equations for our first order, which is this guy. And also our half-life equation would go with it as well, just in case we needed it. Might not need it here in this particular case. So we do have the obviously the rate constant given to us. We do have the time given to us, which is 865 seconds. We do have our initial concentration given to us, and we are looking for our final concentration. So really, in this case, we just need this equation. Sometimes you do need to kind of use them both together, but in this particular case, we do not. We're good to go. We can put everything pretty much in there. So we're going to try to find our kind of final concentration, going to be equal to the natural log of our initial concentration, which is 0.0225, minus our rate constant, which is given to us at 2.9 times 10 to the minus 4 reciprocal seconds, and 865 seconds was our time. Now, I think I mentioned before, but you do always want to be careful, especially when you're using this equation, in terms of the units that you have in both of these locations, really these two guys. Again, sometimes the time is given in perhaps hours, maybe the other time's given in seconds. So sometimes you have an issue in terms of units that these guys will not cancel out completely. You'll need to do some type of conversion. So it's a very common mistake people will kind of do, is they kind of overlook the kind of units there of the time. So you just want to make sure you don't do that. So I'm just going to kind of clean up everything here on the right hand side. I'm going to try to punch it in correctly there. That would probably help too. Natural log of 0.0225 minus 2.9 to the minus 4 times 865. And that gives us the natural log of A. And if we clean up everything on the right-hand side, 4.045089997. I don't feel like rounding today. And to get rid of that natural log there, we're going to E both sides. Remember, when we do that on this side, we pretty much are just left with the concentration. And if we take that E there, we are going to end up with 0.0175 units. Here would actually be the same units as this guy, which would be molarity in this particular case. Any questions on that calculation there? We could also kind of make sure, it sort of makes sense. Remember that this reaction is, proceeding towards the products, which means we would expect this concentration to start to decrease. And we see from the initial to sort of where we ended up, it did decrease. So that does make sense. Again, if you saw it go up, then probably something went wrong there with your calculation. All right, one more sort of first order guy here. So give this one a go. What is the half-life of this reaction? Okay, so looking at this one again, they were nice enough to tell us first order, but we really can figure that out right there by looking at that unit. It tells us it is first order. Since we're dealing with the half-life, we obviously would want to use our half-life equation that goes with first order. They did give us the rate constant, so again, this one not too bad. Just kind of plug and chug into here. 71 reciprocal seconds, and that is going to yield us natural log of 2 divided by 0.271, or about 2.56 seconds would be the half-life here. That is a very fast half-life. That means pretty much every 2.5 seconds, half of whatever you started with is gone. So it goes pretty quick. Any questions on first order stuff here? And again, for the final, you are responsible for through first order. So that would sort of be up to this point is technically what you're responsible for. All right, so let's talk about then some other orders of reactions. The next type of order, which is sort of common, is what is referred to as a second order reaction. And in a second order reaction, you basically could get it one of two ways. You could obviously get it where you have, like we see here, A to the second order. You also could get it if you had, say, two reactants where they were both first order, and that would add up overall to second order as well. So that's another sort of way that you could sort of achieve that. Also, two reactants where one is second order and one is zero order is a third way that you can do that. Now, when we rearrange this guy, this rate law, and solve for the rate constant, and again put our units in, we see something that is common for second order reactions in terms of the units associated with the rate constant. And these are 1 over molar seconds, or m to the minus 1, s to the minus 1. And much like first order, the seconds part doesn't necessarily always has to be seconds. It can just be some unit of time, it could be minutes, hours, days, whatever it may be, but it's 1 over molar seconds. And you can see that is different than 1 over seconds, which is typically what we see for first order. So understanding sort of those orders, understanding the units to go with the rate constant will help you sort of determine the order that you're dealing with. Now, when we look at sort of second order here, it also has its own sort of unique, what is sometimes referred to as integrated rate law, which is this one. And this is 1 over A, which is kind of like what we had before. That is our final concentration, equals 1 over A naught, which is our initial concentration, and K being our rate constant, and T obviously being time again here, not temperature like we had before. In addition, you also see second order having its own half-life equation, different than first order. And this is 1 over K times the initial concentration. So unlike first order, the half-life of a second order reaction is dependent on the initial concentration that you basically start with. So it can have a big effect on whether or not, you will end up with a sort of longer half-life or a shorter half-life. So if you have a, just mathematically thinking about it, if you started out with an initial concentration that is larger, basically be dividing by a larger number, which will give you a smaller number, as opposed to if you had a smaller concentration, you divide it, you'll get a larger number. So again, it will have an effect on sort of the half-life. We could also take this equation, kind of like what we did with the first order, and rearrange it and write 1 over A is equal to KT plus 1 over A naught. And this would be written in the form of a straight line, y is equal to mx plus b. And this is how we get the traditional sort of second order plot that is done. On the y, we graph 1 over the concentration of A. On the x here, we graph time, and that should yield you a straight line where the slope will equal actually K in this case, the rate constant. So here you can see a couple of different things that are sort of important for a second order reaction. First off, we have different sort of equations that go with second order, in addition to different units that are associated with it. So 1 over molar seconds, or 1 over the unit of time, a different sort of concentration and time equation here, and a different half-life equation, and obviously a different plot, actually going in a positive direction, this line, versus first order, which is going in a negative direction. So usually the important things out of second order is sort of the units, the equations, and the associated graph that goes with it. And again, that's why, if you were given a problem where it gave you the rate constant that had these units, you definitely would want to be using these equations here rather than obviously the ones that we saw for first order. Any questions on that there? Another common order of a reaction is zero order reactions. And when we talk about sort of zero order, it's kind of similar a little bit to first order, but a little bit different. How do we get a zero order? Well, we obviously would usually have one reactant to the zero order. And when we take anything to the zero order, it equals 1, right? So if you take anything basically to the 0, that equals 1. And basically that means that the rate equals the rate constant, which means that if we rearrange this equation, the units that are typically associated with the rate constant for a zero order reaction is actually the same as the rate, which is molarity over seconds. So again, you can see different units for the rate constant for a zero order reaction versus a first order versus a second order reaction. Also has its own sort of concentration and time equation. This one pretty much is identical to the first order, except no natural log. So basically, kind of the same thing, except without the natural log. We have our initial concentration, our final concentration. I pointed backwards. Final and initial concentration, rate constant, and time. Also has a different half-life equation. This one as well, the initial concentration here plays a role in the half-life. So if you just think about it mathematically, if you have a larger number up on top or a larger initial concentration, you will have probably a larger half-life than if you started with a smaller number up on top. Again, bigger number up on top divided by a smaller number gives you a bigger number. Small number up on top divided by a bigger number gives you a smaller number. So that has an effect on it. Just like we've seen before, rearranging that equation for a straight line gives us this equation that looks something like this. And this again is y is equal to mx plus b. That means when we do our typical zero order graph, there on the y is the concentration, much like all the other ones. On x is our time, going to yield us a straight line with a negative slope, and that means the slope is equal to minus k, because the slope will be negative here and this will be negative. That will turn our rate constant, which is usually a positive number in this case, because of that. And that's typically what you get. Now you may be looking at this graph and go, I think I saw that was first order. And we did see that graph with first order, which was the concentration of A versus time. But what we saw with first order was not a linear relationship. We saw this sort of decreasing with time relationship, first order. So although they are the same two things that are graphed, this graph down here is for zero order, which gives us a linear relationship, versus when we do that graph there and we don't get that linear relationship, we get that sort of decreasing with time sort of relationship. That is for first order. So those are the same graphs, but the resulting sort of graph or plot is different. One is a straight line and one is obviously not a straight line in this particular case. Now, just like the other ones, really, when you think about these guys, sort of the important things are the units associated with the K, obviously the rate law, the half-life equation, and the graph here, are usually the four things that are sort of important. And again, obviously, seeing these units are told that a second order should take you to these equations here rather than our sort of first, zero, or second order. So you may be asking yourself, why are there other orders? And the answer is, yeah, there could be technically other orders. But if you think about most reactions that you deal with or have seen, when you think about sort of the reactants, for example, it's maybe one reactant decomposition, maybe it's a couple reactants. So, if you think about sort of the combinations that we typically get, maybe this guy is one first order, second order, zero order. Maybe each of these are first order, or one's second and one is zero, or something like that. In order to get maybe some orders greater than, say, second order or so, third, fourth, whatever order it may be, you probably are going to need multiple reactants, more than two. And in most reactions, you know, most of the time you top out about two reactants, maybe three reactants. So it's very unusual to have a reaction where you dump in like three or four or five or six different reactants together. So usually, in most cases, we're obviously in this sort of range in terms of how many reactants, which obviously in most cases will limit our orders or overall orders of our reactions to zero, first, or second order as sort of common overall orders that we get. And again, in theory, you could definitely get obviously like a third order or something like that. But the reality of, going third, fourth, fifth, sixth order or something like that, probably a little bit more unlikely to occur because of probably the necessity of a lot of different reactants sort of happening. And again, in most cases, we usually just start with a couple, maybe, or one sort of reactant. Any questions on that there? Okay, so let's take a look here. So it is second order, and we're trying to find the rate constant. So because it's second order, again, we would want to go with our second order equation, which is different than first, and as we just saw, also different than zero order. It actually has a plus in there as well, which makes it a little bit different. In this case, we have our initial, and we do have our final, and we do have the time, which is in seconds. We're trying to find the rate constant. So we really could just plug it in there. So our initial would be, I'm sorry, our final would be 1 over 0.0010 is equal to our initial, which is 0.010. I got all the zeros there. Plus the rate constant, which is what we're looking for, and our time, which is really 500 seconds in this case. Obviously, in this case, they would need to tell you that it's second order since they are not, you're trying to find the value of the rate constant, and you would have no other way of determining what order it was if they didn't tell you that. So again, mathematically here, we take 1 divided by 0.0010, which is 1,000, and which is this. And then we're going to subtract that guy to the other side. So at that point, I'm going to subtract 1 divided by 0.01, and that's going to give me 900 when I do that. And that will equal K times 500 seconds. We're going to divide that to the other side. It's actually 1 over molar seconds. And we take 900 divided by 500 to the other side, going to give us 1.81 over molar seconds would be the units, which are the typical units that we would associate with our rate constant for a second order reaction. Again, basically, this is the unit on both of those. So when we bring them over, we basically end up with 1 over molar seconds. And when we divide the seconds to the bottom, that's how we end up there with our 1 over molar seconds. Any questions on that one there? Okay. So here's a nice little table of the different sort of integrated rate laws or concentration time equations and our half-life equations. And again, you can see depending on the order, you can have very different sort of equations. So again, for our final, you are responsible for this right here. Okay, obviously we talked about sort of the graphs that are associated with these. So in addition to obviously having different types of equations for first, zero, or second order, there's also those different graphs. And that's a very common way, sort of in kinetics experiments, sometimes to figure out the order of a reaction is to actually do each of those graphs. So if you wanted to kind of determine a reaction, you weren't sure, what order it was, you literally would just graph the information as the natural log of A versus time. You would graph 1 over A versus time, and you would graph A versus time. And what you would do is basically look and see which one is the most linear. And if you're doing something like Excel or something like that to do these graphs, you would look at the linear coefficient, which is r squared, and r squared value closest to 1 is like perfectly linear. So in comparison, you would usually do something like on Excel like this, and you'd find the r squared value is like 0.999. R squared value is like 0.989. R squared value is like 0.922. Made up these numbers. And you would go, okay, this guy is closest to 1, so this is the most linear. I know this would then be first order. And again, that's a very common way, sort of graphically, that we kind of determine, the order of a particular reaction. So now we're going to talk a little bit about, good talk, we're going to talk a little bit about temperature and energy and sort of the reaction rate and what happens with it. These are two sort of energy diagrams, and this is a exothermic reaction over here. Remember, exothermic delta H value is a negative value, means that heat and energy is released. And how do I know this is sort of an exothermic reaction? Well, when I look at the energy of our reactants here versus the energy of our products, I see that the reactants are higher in energy than our products. So, in order to sort of get down there to our products, energy has to be given off or released for those guys to basically get down in terms of energy to our products. And that's a classic exothermic diagram, as opposed to an endothermic diagram where we have over here on the right, which means heat and energy is absorbed. Also means that the delta H value is usually a positive value. And how do I know the difference there? Well, we see the exact opposite here. The reactants are lower in energy than the products, which means in order to kind of get ourselves up there, we got to put energy in to sort of get ourselves up there as well. Now, when we look at this reaction, there basically is a minimum amount of energy that's required really for a chemical reaction to occur or to initiate a chemical reaction. And that's really this hill here that has to be climbed to get to the other side. And if you look at this hill, it's right here. This is the activation energy. And over here, this guy here, this hill right here, is the activation energy. Now, it's important to remember, and sometimes we think about it sort of differently, but we think that if two things sort of come together and they collide, which is sometimes referred to as collision theory, they basically bang into each other, that's going to sort of have a reaction occur and products would be made. So if we had two reactants sort of come in collision with each other, we would expect perhaps products to be made. And that's not always the case. So there's actually two things that really need to occur in order for products to sort of be made. And that is they do have to obviously come in contact with each other, but they do have to come in contact with each other sort of in the right area, like the active site, if you will, in order for that reaction to take place. And they need to come together with the sufficient amount of energy for a reaction to take place, which is essentially that activation energy, enough energy to get everybody up and over the hill. So what happens as this reaction progresses and sort of goes on, these reactants sort of start climbing the hills. And what ends up happening is we start to get these guys that are going to basically start breaking bonds, right? That's basically what happens in a reaction. We got to break all the bonds. And then at the same time, they're going to be starting to make some bonds as they kind of head over towards our product side. And they will eventually reach the top of the hill here. And the top of the hill here is what is sometimes referred to as a transition state. And this is what is sometimes referred to, this little guy AB with the little kind of symbol there. This is what is sometimes referred to as a transition state complex or an activated complex. And what is that guy? Well, that guy is something that is pretty much at the peak of energy. And when we think about things in terms of energy, things in high energy, as we talked about in the semester, are not very stable. Things really don't want to be in the highest energy, kind of like when we talked about electrons going to those high energies. They really don't want to be there, right? They want to come back down to sort of a lower state of energy. And it's sort of the same idea. We get this guy, which is sort of like an intermediate. It's very high in energy. Is actually something that has sort of partially made bonds and partially broken bonds happening. So it's kind of like this little transition guy that is going from where we were in terms of our original bonds to starting to transition into making some of those new bonds. Because it's really high in energy, it doesn't hang around very long. It's not very stable. And it usually relatively quickly will kind of drop down the hill towards the product side in that case. And when we look at sort of the comparison of an exothermic reaction to an endothermic reaction, we could see very clearly that a exothermic reaction typically has a smaller hill to climb than an endothermic reaction, which means why it's endothermic, you might need to put some energy in there to get everybody up and over the hill to the other side. How does that sort of hill or activation energy basically relate to the rate of a reaction? Well, if you just think about it, just logically speaking, if you had to walk a big old giant hill to get to the other side versus just like a little bump, you probably would get to the other side a lot quicker. More people would be able to get to the other side a lot quicker, and you probably would have a much higher rate than if you had to kind of go up this like vertical hill and then kind of go all the way up and over to the other side. There may be people that can do that, but there probably would be maybe a smaller percentage of people that can go up and over the hill. Going to take a little bit longer to get all the way to the top and over to the other side. And again, that obviously would result in a probably slower overall rate of a reaction. So the activation energy is that sort of barrier, sort of the thing that for the most part, a lot of times will determine a lot of how fast or how slow a reaction will actually take place. Any questions on that there? So there actually is a relationship between sort of temperature and the rate of reaction, as we talked about before. If you just think about it sort of logically, if we increase the temperature, typically what we would do is see an increase in the rate of a reaction. So why is that? Well, if we increase the temperature, we're going to get obviously people that have a lot more energy. A lot more energy means that when they do come in contact with each other, they're going to have a sufficient amount of energy to get up and over that hill to get to the other side, which would result in probably more products being made at a faster rate. In addition, having sort of that more energy means that they're going to be moving around a lot faster, which means, again, they're going to come in contact with each other a lot faster than if you did the opposite and you threw everything on ice. Throwing everything on ice, for example, take your test tube, if you're doing the reaction in a test tube, plump it into like a bath of ice. What it's going to do basically is kind of remove a lot of energy, which means things will start moving slower. You'll have a lower proportion of people that when they do come in contact have enough energy to get up and over the hill to the other side, and you typically will see the rate of the reaction kind of decrease. This is the Arrhenius equation here, and it's basically our rate constant. This is what is referred to as the frequency factor, which we'll talk about, but basically it's the percentage of molecules that do have sufficient amount of energy to get up and over to the other side. The E of A is our activation energy, which is that hill that they have to climb. By the way, the activation energy usually is a positive number. So when we look at this, right, this is the activation energy going upwards, and it's a endothermic type thing, and it's usually positive. This is actually the gas constant, but it's actually the one that involves energy. It's the 8.314 version of it, as we see here. And T is our temperature in Kelvin. Much like most things, it does need to be in Kelvin. This is one version of the equation. We'll see probably a more useful version of the equation here, but again, this is sort of the energy that's happening. Basically, we've got to break all these bonds. We need to make new bonds. And again, as that's happening, that's transitioning to where we get this sort of intermediate where we got partially made and broken bonds, sort of at the height of energy, which is very unstable. And then it sort of transforms into our products as it drops down this hill. This would be an example of reactants are higher in energy than products. This would be an example of a exothermic reaction, heat and energy being given off in this case because of that. Now, the activation energy in the activated complex, as I mentioned, is really that barrier that everybody's got to kind of climb to get to the other side. And we really do get that sort of high energy complex at the top of that hill where we really do have that, why it's called a transition state, that transitioning of reactants and their bonds into the bonds making of the products. And again, that's why I sort of refer to as a transition state. It's really where that transition sort of occurs, where everybody kind of breaks their bonds and starts making their new bonds. Now, taking that Arrhenius equation here, we do see a couple of relationships. And the first relationship is if we graph the rate constant versus temperature, what we see is at a lower temperature, a much lower rate. I guess a slower rate would be a better way of putting that, at a low temperature. And we do see that as we increase the temperature, we put more energy in, and we end up with a much faster rate, or higher rate, I guess is another way we could look at that. So again, there definitely is that relationship. And more important, more commonly, when we look at the Arrhenius equation, we actually take the natural log through this, and we end up with this one here, which is really sort of the graphical version of the Arrhenius equation. And that again is the natural log of K is equal to minus E of A over R, 1 over the temperature in Kelvin plus the natural log of A. This is written in Y equals mx plus B. And the typical graph that we graph for this plot is the natural log of K versus 1 over the temperature in Kelvin. And when we do that sort of plot, what we see is a plot that looks like this. And the importance of that y is equal to mx, oops, mx plus b, is that the slope will equal minus E of A over R. So if you do this plot, and you would do this plot if you had a bunch of rate constants at some different temperatures, you would take the natural log of all the rate constants, and you would take 1 over the temperature in Kelvin, and you would do this plot. It will give you this line. And what you will end up with is you could get the slope of that line. And graphically, you would be able to determine the activation energy. By the activation energy would equal minus R times M. Since this line has a negative slope to begin with, the negative and the negative will turn our activation energy into a positive number. So it is going to be a positive number, as we just talked about, sort of that hill that they have to climb, and that is sort of a positive aspect of it. So this is a more common sort of use of this equation. Again, graphical sort of use of it, and it allows you to figure out things, but mainly you would do this to sort of graphically figure out what is that activation energy for that particular reaction. Any questions on that there? So as I mentioned before, looking at this equation, we do see a couple of X things that we talked about, but basically sort of that fraction of molecules, sort of that A guy, frequency factor is that proportion of molecules that really do have enough energy to get up and over the other side. And basically what we see is what we saw in those couple of graphs here a second ago. If we increase the temperature, we increase everybody's sort of kinetic energy. It's going to allow things to react a lot quicker and a lot easier. And we would see again a bigger proportion of molecules being able to get up and over to the other side. Kind of like that old saying, light a match under somebody, right? They move very quicker. Same idea here. If you increase the temperature, they have more energy. They're able to kind of move over sort of to the other side a lot quicker. And obviously, as we also talked about, vice versa would be if you lower that temperature, you're basically doing the opposite effect. You're causing less molecules having the sufficient amount of energy. And that's what we see here in the comparison of temperature 1 and temperature 2. Temperature 1 being the blue graph, and temperature 2 being the red sort of curve there. The red curve is a higher temperature than the blue curve. And if we look at where the activation energy is, which would be this line, if we look at the blue temperature, which is the cooler temperature or lower temperature, really only this much or fraction of molecules have enough energy to basically get up and over that hill. By basically increasing the temperature, what we see happen is, in addition to that much, we then have this much more available up there basically to increase and get up and over to the other side. Again, by adding that extra energy, by increasing that temperature, we get a greater proportion, almost half more in this little diagram roughly, that has a more energy or enough energy to get to the other side. So again, increasing that temperature really does have an effect there on what we see in terms of um, how fast or slow reaction take place. We do want to be careful. We do anything mathematically with this sort of equation. That's with units. And R, which is the gas constant, has units of joules, as you can see here. And typically speaking, the units of activation energy is usually kilojoules. So if you ever do anything mathematically with sort of this equation, or one we'll see here in a second, you do want to be careful of units so that you make sure you end up with sort of the right units and not off by a factor of 1,000. By the way, graphically speaking, the natural log of A is plus B. So the y-intercept of that graph equals the natural log of A. So you could also graphically determine, in addition to activation energy, you could also determine the frequency factor. Are that proportional molecules that really do have enough energy to get up and over to the other side? Any questions on that there? So just to show you sort of a sample of, how you would go about doing this. This is a table of obviously data that would be collected. And if we wanted to kind of determine the activation energy, which is E of A, and the frequency factor, which is A, we would need to do a graph. What we would need to do is basically take our temperatures here, and they happen to already be in Kelvin. If they weren't in Kelvin, we would need to convert them to Kelvin. And we basically would want to take 1 over the temperature value for all these points on both sides. We then would want to take our K value and take the natural log of the K value. And those would then represent, obviously, the points that we would graph. And if we went to something like Excel or something like that and did that graph, again, you can see that linear relationship that occurs when we do the Arrhenius plot. And we get this equation for the straight line that would come from, obviously, the graph. So a couple of things, right? Remember that when we look at the equation, we have our natural log of K is equal to minus E of A over R, 1 over T, plus the natural log of A there. Getting old there. And again, this equals Y is equal to mx plus B. So first off, if we want the activation energy, that would be basically from our slope. So we would see that the slope is equal to minus E of A over R. And the slope value would be this guy right here, including the negative. So that would be what we would use. And that's what we were talking about earlier, that it is negative, and then our line is also negative, which will always give us a negative value there for the slope, divided by our 8.314 joules. And since we're dividing by the gas constant there, which is in joules, we will actually end up with an activation energy that is in joules, except that I did not do that right. So when we do the math part of that right there we go. Let's actually maybe do the math part right. So we're going to multiply R to the other side, which will leave us our E of A, and we're going to multiply it by R here. That would be better. Again, multiplying R to the other side. And now if we do that correctly there, that's going to give us something like 93116.8. Again, the units here would be joules. Since it is typically given in kilojoules, divide by 1,000, move it over 3 places, gives us something like 93.1 kilojoules. Again, positive number because it is the activation energy in this particular case. Any questions on that calculation there? So in addition, we can figure out the frequency factor, which is this part of it. And that means that B is equal to the natural log of A. B would be our y-intercept here, which is 26.8. So that would give us 26.8 is equal to the natural log of A. To get rid of that, we're going to E both sides there. And when we do that, we end up with 26.8. Looks like 4.36 we'll go with. So A would equal 4.36 times 10 to the 11. And you might be wondering what the units will be. The units actually will be the same units that we see for the rate constant. And that's because when we graphed this, we took the natural log of k, which got rid of the units. But in the end part there, we took the e of it, which got rid of the natural log. And long story short, too late for that, I suppose, we come back to basically the same units that we started with in terms of our rate constant. So that would be reciprocal molar seconds here. Question on how to use the graph information there to figure out the activation energy or the frequency factor there. Now, really, who wants to, make graphs all the time? Nobody does, although it's kinetic. So graphing and sort of using data is very important. But there is actually a more sort of useful version of this equation, which is sometimes referred to as the 2-point form. The 2-point form basically means that line that we just saw in that graph, for example, you take 2 points off that line and you basically can figure out kind of the same information. So this is one version of this equation. If you ever look around, there's actually like 3 different versions of this equation that's floating around. Somehow the negative distributed on the outside, which means the inside here where the temperature is kind of flips around. Sometimes they will combine the bottom there, T1 times T2, and sort of a common denominator sort of move. But this is one that you commonly will see in terms of the formula as well. And these are sort of our same things that we've seen before. These are 2 rate constants at different temperatures. So these are rate constants at different temp. And that means that obviously T1 and T2 are different temperatures, and they do need to be in Kelvin. E of A is our activation energy, which again, as I mentioned just a second ago, unit-wise, a lot of times is given in kilojoules. So again, we want to be careful on that. Then R is obviously our gas constant, which has units of joules. So this sort of version of this equation is the one where you do want to be careful because you do have those different units that can sort of mess things up. But this allows you, if you know maybe 2 rate constants and 2 temperatures that they're associated with, you can figure out the activation energy sort of mathematically without graphing. If you know the activation energy and maybe 2 rate constants and 1 temperature, you can figure out what the other temperature would be, and vice versa. If you know the activation energy, 2 temperatures and 1 rate constant, you can figure out what the other rate constant would be. So sort of a useful sort of equation that you can mathematically sort of determine these things. So why don't you try one here and see what you come up with. We're looking for the activation energy. Go to E of A over R, 1 over T1 minus 1 over T2. In terms of our temperatures, they're already in Kelvin, which is nice. If they weren't, we would have to sort of convert it. What you just want to make sure, it really doesn't matter sort of which one you call 1 and which one you call 2. Most people just kind of go with how it's in the sort of problem. If we do that, then K1 in this case would be 2.57, and that would obviously go with T1, which is 701. And then K2 here would be 567, and our T2 that corresponds to that is 895K. We see an increase rate in the rate constant as the temperature went up from 701 to 895, increase in the temperature, increase in the rate constant that we see here. So again, it doesn't really matter as long as you kind of keep the correct rate constant and temperature together. Other than that, I think that's pretty much all we need. We could go into here. We're going to do the natural log again of K2, which is 567 divided by K1 is equal to E of A, which is the activation energy. That is what we're looking to find, divided by R, which is a constant. And now 1 over our T1 in Kelvin, which is 701, minus 1 over our T2 there, which is 895. And at this point, we could do a little bit of cleaning up. We'll clean up the right-hand side. We'll clean up the left-hand side as well. And if we do some of that, we end up with also a very common mistake here is you want to divide first. So 567 divided by 2.57 and then take the natural log of it. And that gets you 5.3964 is equal to E of A over our R. And if we kind of clean up what's inside there, 1 divided by 701 minus 1 divided by 895, I think it was. And that's going to give us 0.000309 here. We then are going to multiply the 8.314 to the other side and then divide. So we're going to multiply this to that side and then divide by that guy, basically. So if we do that, we're going to take 8.314 times our 5.3964, gives us about 4486 divided by 0.000309, going to yield us an activation energy of 145,196. The units here would be joules based off of the joules from the gas constant there. And that would be our activation energy. That typically would then probably be brought down to about 145 kilojoules, as our activation energy is typically given in kilojoules. Any questions on that calculation there? All right, so again, this is sort of the Rayleigh equation relationship between temperature and the rate. And again, as I was mentioning just a second ago at the beginning here, our temperature went from 701 to 895. We increased the temperature and we see a pretty dramatic increase in the rate here, right? It went from 2.57 basically to 567. And we do see that pretty good increase in the rate of this particular reaction. All right. So this again was sort of showing what we were talking about earlier, that not all collisions will necessarily result in products being made. So if we look at this here, we can see that when we sort of collide our potassium here and our methyl iodide, when the purple side, which is the iodide, and the potassium come in contact with each other, that's going to produce our potassium iodine, and we will get some products that are made and some methyl group. But if we sort of have the potassium and the carbon, which is represented here by that circle, we end up with actually no products formed. So just the act of two sort of reactant molecules colliding does not necessarily guarantee that you're going to get products being formed. Again, as we talked about, you need basically them to hit each other in the right sort of location, if you will, like what we see here. And they need to obviously hit each other with the sufficient amount of energy in order to form products. Just simply that collision is not necessarily always going to guarantee that you do get products. Now, the last thing we're going to talk about here is what's referred to as reaction mechanisms. And it's a reminder of a couple of things that's important. And since we didn't really talk about it in this class, you'll talk about something known as Hess's Law, probably in 200B, when you go backwards to chapter 6, I think, in our book, and talk about energy. But not all reactions happen in sort of a one-step process. So what I mean by that is we have, say, an overall reaction of A plus B going to E plus F. We're sometimes tempted to believe that, this is just going to go directly from there to there in sort of a one-step sort of process. And that's not necessarily always the case. It may actually occur in multiple steps. Maybe what will happen is like A plus B will first form C plus D, and then maybe C and D react and form E plus F, learning the alphabet there. And if we add both of these reactions together, we could cancel out what's the same on opposite sides of the arrow, kind of like what we did in redox reactions. So the C here and the C here will cancel out. The D here and the D here will cancel out. And that will leave us the overall reaction of A plus B goes to E plus F in this particular case. And we can see here that in the overall reaction, we don't see anything involving C and D in my example. But it is definitely there in this process. So those guys are what are referred to, as we will see here in just a second, was referred to as an intermediate. It is something that's sort of made early on in a mechanism, and it gets kind of used up in a later sort of step. So Not all reactions are sort of a one and done sort of situation going from reactants to products. It sometimes is two steps, sometimes three steps, maybe multiple steps to get to the sort of overall reaction. And sometimes, we oftentimes just sort of look at overall reaction. So we very sort of subconsciously think, okay, it always just happens like from reactants to products, but not always the case. So that's where sort of reaction mechanisms come into play. Reaction mechanisms are sort of these individual sort of steps that lead to a product being formed. And these kind of individual steps along the way is what is sometimes referred to as elementary steps. And it gives a whole reaction when you add them together and a reaction mechanism, which is basically a plausible explanation for how a reaction could occur. It doesn't necessarily mean that this mechanism is 100% always how a reaction occurs, but it's some way to sort of explain how this reaction sort of takes place. Now, when we look at a real reaction, something like this, where we take 2NO and O2 and make NO2, while this reaction is taking place, you could detect N2O2. And clearly, if we look at the reactant side and we look at the product side, there's absolutely no mention of N2O2. But it definitely is sort of seen as this reaction is taking place, which would imply that it has to be made but then used up completely before the reaction is over. So a proposed mechanism for this one involves a couple of elementary steps where maybe in the first step here, a couple of NOs come together to form that N2O2, which is why it could be detected during the process. But then almost immediately, that N2O2 then goes through a reaction and kind of gets used up and forms our NO2. And these guy here is going to be our intermediate in this particular reaction. And again, this is a way to sort of explain, why we see the N2O2 during this reaction, but we don't see it sort of represented in the overall reaction that's taking place. And again, we can cancel out that N2O2 as an intermediate. Here's just a graphical version of that. So the importance, though, of an intermediate is a couple of things. First off, it is the idea that it does get formed early on in a sort of reaction mechanism. But the importance of what makes something an intermediate is it should not appear in the overall reaction. So you will sometimes, when you look at mechanism sort of problems, you'll sometimes see things that cancel out, but do not cancel out completely, and they're still there at the end of the reaction. And those things, although they do cancel out a little bit, because they did not cancel out completely, are not considered intermediates. They do have to cancel out pretty much completely for that to be the case. So here again, our N2O2 cancels out completely, which would be an intermediate. And we can sort of describe each of these elementary steps by how many molecules are reacting. If something is unimolecular means one molecule is reacting. Something is bimolecular, that means two reactants are reacting. And something's termolecular, that means three guys are reacting. In this example here, there are two guys reacting. This would be bimolecular. There are two guys reacting here. This would also be a bimolecular elementary step. Now, if you remember early on when we talked about determining rate laws and stuff like that, and those orders, when we write the sort of rate law, if you remember, we said that they are not based on the coefficients in the balanced equation. The one place where you can actually write a rate law and use the coefficients is when you're doing mechanism. And that's really the only place that you could do it, is when you're doing mechanism type problems. So if we were to look at some of these elementary steps, we could actually, for every elementary step inside a mechanism, we could actually write a rate law. So for a unimolecular, coefficient here is 1. We could say the rate is equal to k times a to the 1. Coefficient here is 1. Coefficient here is 1. We could write a rate law for this step as the rate is equal to k times a to the 1 and b to the 1. Here, this is basically the same as 2a, which is where the 2 comes from here. And again, just to be very clear, this is the only place you can use the coefficients as the exponents, are the orders. What we were doing at the beginning of this chapter, you cannot do that, and you should not do that for our final, because you would be doing it wrong. So you should not do it at any place other than when you're dealing with mechanisms, which obviously will not be during our class, but it will probably be during maybe the final next year, when you, because they usually do a lot of kinetics on your final in the next class. Um, so you will can use those coefficients here. So how do we know, though, if we look at a mechanism, if a mechanism is perhaps a good mechanism or a bad mechanism? And there's basically two really important things that you want to look at when you think about a mechanism as to whether or not it is possibly a good one or a bad one. The first one's pretty simple. When you take all of the steps that there are in a mechanism, maybe 2 steps, maybe 3 steps, 4 steps, however many steps, and you add them all together and you cancel out whatever's opposite sides of the arrows, that cancel and everything. If you are left with the overall reaction you're looking for, then it's a good mechanism. Now, if you add up all those steps and they do not equal the overall reaction you're looking for, then it's a bad mechanism. So that's one thing that has to happen. The second thing that has to happen is the rate law for the rate determining step should be the same one that's found experimentally. So very common in mechanism problems, they'll tell you in the actual problem, hey, experimentally the rate law was found to be this. And what that will tell you is when you look at all the steps in the mechanism, there should be a rate law that matches it completely and exactly. And that will tell you that is your rate determining step. Your rate determining step, which is sometimes abbreviated as the RDS, is what it says here. It is the slow step in the mechanism. It is the one that, based on that mechanism, is going to cause the longest time for that part of the reaction to occur, is the slowest part of the mechanism, and it's really the one that's going to determine how fast overall that reaction would occur. How do you determine it is the rate determining step? Well, there's two ways. They will either tell you next to it that, hey, this is the slow step, and that's a very good way to know that is your rate determining step. Or again, they will give you the rate law that was found experimentally, and it will match one of the rate laws that you see in the mechanism. So let's take a look at one here just to finish up on. So if we look at a kind of simple mechanism type problem here, and we want to know a couple of things. We want to know, what is the overall reaction that's happening here? What is intermediate, and what do we know about what's happening in this mechanism? So first off, this is a mechanism that has 2 steps, and if we want the overall reaction, we basically would just add these together. And when we're adding these together, again, anything on opposite sides of the arrow will cancel, either completely or reduce down. So one of those will cancel. And what we're left with, just like we did with redox, everybody on the left-hand side of the arrow stays on the left-hand side. Everybody on the right-hand side of the arrow stays on the right-hand side of the arrow. And that would give us our overall reaction that is happening in this case. What is the intermediate in this case? The intermediate in this case is NO3. Now you may be saying to yourself, wait a sec, didn't we cancel out a couple of things? And you would be right. We canceled out this guy and we canceled out these guys. But out of those two, it was only the NO3 that completely canceled out, because the NO2 is still found in the overall reaction. It is not considered an intermediate. So remember that in order for it to be considered an intermediate, you need to have it be made early on in a mechanism and completely used up. Now, what can we say about the rates of each of these guys? So again, because this is a mechanism and this is the only place that you could do this, I'm just going to erase some of this stuff here. We could actually write a rate law for each of these steps, and we could use the coefficients to help us. We could say for step number 1, the rate would equal K times NO2, and we would square it because essentially this is 2NO2, so that 2 is where that 2 comes from. Again, the only place we could kind of use the coefficient is in this type of problem, mechanism problem. And the rate here for the second step would be K times NO3 times CO. Now, if you remember the rate determining step, which is the slow step in the mechanism, will have the same rate law as the one that was found experimentally. So we could see that experimentally, the rate law was found to be the rate is equal to K times NO2 squared. And that matches perfectly the rate law that we see for the first step. So, because those two match perfectly, what that tells us is in this mechanism, step number one is our slow step, our rate determining step. And that means that step one is slower than step two. Step two in this mechanism is going to be the one that occurs a lot faster than step number two. And just to kind of show you, I guess maybe I could draw it. I'll do it here. So in this particular case, what that means is we're trying to draw sort of an energy diagram really badly here. But if we drew an energy diagram, we would have step number one and something like this. So this would be step one here, for example, and you can see the activation energy here, the hill that you have to climb for step number one is very big compared to down here. This would be step number two. It's a much smaller hill. So in this sort of example here, we would have our NO2 and coming across to our NO3 and our CO, and then it very much quickly converts to our NO2 and our CO2. But the first step is a much bigger hill, going to take a lot longer for those guys to get over. But as it comes back down, it's going to have a much smaller hill to get over to get to our products. And that's the idea behind this, is to explain that sort of reaction, how it's occurring. And based on this, what we see is step number one would be our slow step because it has a matching rate law to the one that was found experimentally. Any questions on that? All right, I think that's good there. That is the end of it, I think. Congratulations. That is the end of 200A. That will be it. Again, a reminder, a couple of things. You are responsible for this chapter, again, through basically first order. So everything involving first order, including half-life and all that. And obviously the stuff that we did previously last week in terms of that lecturing. The rest of this hopefully will be helpful. I don't know. I've been a bit since I've done 200B, but years ago in 200B, your final used to have a lot of kinetics type stuff on it. So hopefully it'll be helpful for you for that as well. The final will be Thursday. We will do it at the start of lecture at 5:30. You do need to take it at that time. Do not email me with any type of story. Yes, you need to take it at 5:30. It will be comprehensive over everything that we've covered. So all the chapters. So I guess that would be 11 chapters, I suppose, we covered, except for chapter 6 we skipped, which is energy, I think. So everything is fair game. I'm not going to purposely sort of focus on one topic more than something else. So I think overall, and I haven't written in yet, so I know I got a day or so to go. But I think it should be pretty comprehensive over everything. Clearly, I won't be able to obviously test you on every single little thing. There may be some things that may be combo, some topics and that type of stuff. But it will be a same format pretty much as our regular exam. So I would anticipate there would be a multiple choice sort of section, and there would be a sort of written section. Anything that you were previously given to you on exams or quizzes or stuff like that would once again be provided to you, including obviously periodic table conversions and those type of things. Anything that you were responsible obviously for knowing previously for exams or quizzes, you are still responsible to know, obviously, for the final as well. But again, I think it will be pretty comprehensive. And